So today we start Fourier series. I think we did the proper introduction. Remember, we started by introducing or reminding you of the Maclaurin series, the idea of Maclaurin series. How did we get the formula for the Maclaurin series? Then we talked about periodic functions. So today we start the Fourier series. First of all, what is the main idea? So there is a main idea in this topic. The main idea is to estimate periodic functions using sines and cosines. So this will be the main idea. If you have a periodic function, now when we say a periodic function, the first thing that comes to my mind is sine and cosine. However, periodic functions are not necessarily sines or cosines. They could be tan, they could be secant, there could be many things else, we will see. Now the idea is I want only to use sines and cosines and to find estimates for these periodic functions. At this point, I like to remind you of the main idea of the Maclaurin series. So if you remember, the Maclaurin series main idea is to find estimates, to estimate infinite differentiable functions. So if you have a function that can be infinitely differentiable at 0, for example, so to estimate infinite differentiable functions using what? Using polynomials. So if you remember, for example, just to remind you, e to the x was this simple form that I assume that everybody remembers this form, okay? So what do we mean by estimation using polynomials? That means if you are interested in computing e to the x and you don't, let's say, have a calculator, or you want to compute an integral using Maclaurin series, then you can take some part of the Maclaurin series. So you say, okay, e to the x is approximately equal to this quantity, which is a polynomial. This was the idea of Maclaurin series. So today we start talking about sines and cosines and how they are used to estimate periodic functions. First of all, we're saying that polynomials are used to approximate infinite differentiable functions. That's done via the Maclaurin series. The first thing, I want to introduce some little definition. So a trigonometric polynomial is a function of the form. So when we say polynomial we know it. It's x squared, x cubed, and so on. Now, when we say a trigonometric polynomial, we mean something very similar, but it's not exactly like that. What do we mean by trigonometric polynomial? We mean f of x equals a constant, let's call it a naught, plus a1 cosine x plus a2 cosine 2x up to a certain number, say an, or let me call it a big N cosine big N x, plus the same quantities for sine. So b1 sine, b2 sine 2x up to b n sine nx. Okay? For example, if you say f of x is a number plus, what do you mean by the a's and the b's? These are just numbers. So for example, plus a number times cosine x plus another number times sine 2x. For example, this is a trigonometric polynomial. So simply, what we mean by a trigonometric polynomial is a finite sum of cosines and sines multiplied with constants. That's it. In this case, if you want to look at this definition and apply it to this function, and if I ask you what is big N in this example, the big N is like the last term, which if you agree, 2. So sine, you see this number here, this is the largest number, so N is 2. In this case, what is A1? What do we mean by A1? A1 is the coefficient of cosine 1x, so in this example it's 2. What is A2? A2 is the coefficient of cosine 2x. So in this example, it's 0. What's b1? b1 is the coefficient of sine 1x, which is 0 in this example. And what's b2? b2 is a 3. Okay, so this is again the meaning of a trigonometric polynomial. This is very similar to polynomials, but polynomials are powers of x. So you have x squared, x cubed. Now you have coefficient of x with sines and cosines. So you have cosine x, cosine 2x, cosine 3x up to a certain term. That's the big N. So for example, you have 100 terms, 1,000 terms, like the polynomials. Remember, for polynomials, you only have finitely many terms. Okay. Now let's say, so if you agree, a trigonometric polynomial can be written in the form, so you have a constant a naught plus the sum a, let's say k, or let me use a sub n, that's more common, an cosine nx plus bn sine nx. Okay, so and the n is from 1 to big N. This is exactly this. Okay, this is exactly this. Okay, so this is a trigonometric polynomial. Now let's do what we did with polynomials and Maclaurin series. Remember when we started this chapter and when we introduced and reminded you of the Maclaurin series, remember this page. So we had a polynomial, then we had these computations to show you how we found this form. Remember, this was the form in the Maclaurin series. How did we find it? These are the computations. So if you start with a polynomial, then you can apply these computations to reach this form, and this is the motivation behind the Maclaurin series. Now I want to do the same thing, but for trigonometric polynomials. So what I want to do now is, you have a trigonometric polynomial like this. So let's find, so now what I want to do is to find a formula for a naught, an, and bn. So can we have a formula? Remember, in the Maclaurin form, in the polynomials, just to remind you here, we had, for example, a naught f of 0, we had a1 f prime at 0, we had a2 f double prime at 0 over 2 factorial, and so on. Do we have the same thing now? For example, if someone says, okay, let me, in this example, in the trigonometric polynomial case, if someone says, okay, let's plug 0 into that function up. So what is f of 0? It's clearly a0 plus the sum an cosine 0 plus bn sine 0. But sine 0 is 0, cosine 0 is 1. So basically what you're getting is a naught plus the sum of an. That's not a naught. That's none of the a's. It's not a1, it's not a2, it's the sum. So f of 0 is giving you the sum of all the a's. This is not what we want. So now what I want is sorry, to have one formula for a node, a formula for a1, a formula for a2, and so on. Let's see how we do this. So I'm doing this in steps. The first thing, let's integrate from minus pi to pi f of x dx. You will understand the idea. You will get the idea, I'm sure. So if you integrate from negative pi to pi, what is, so let's do some little computations here. Sorry, I'm still having this flu for 3 weeks. This is too much. So if we, just to remind you, the integral from negative pi to pi cosine and x dx. So I'm doing these computations here. So how do you integrate? Now, what is the little n? The little n values are from 1 to big N. Okay, so for example, if the big N was 100, you're talking about from 1 to 100. So how do you integrate the cosine? The integral of cosine is sine over n from negative pi to pi. And if you plug the upper and lower values, you get sine and pi and sine negative and pi, which are both zeros. So when you integrate cosine nx, you get 0 from negative pi to pi. Remember, this is what is it? This is very similar to what we did in the first chapter of the course when we had some integrals, some trigonometric integrals. This is the cosine function from like this. If you talk about the interval from negative pi to pi, this is the cosine function. So now if you look at the integral from negative pi to pi, you have this negative area, which is exactly equal to this positive area. So when you integrate over minus pi to pi, basically the positive and the negative areas cancel each other and you get 0. This is our understanding for this 0. Then what about the integral from minus pi to pi of sine nx dx? Similarly, it will be 0, but again, I like to show you this little graph again. So if you draw the sine from negative pi to pi, it will be something like this. So again, if you look at the interval, this is the negative of this as areas. So when you integrate from negative pi to pi, of course, you will get 0. Okay, this is, of course, if n is 1, 2, and so on. Now going back to our integral, so if we go back to this integral here, so this is the integral from minus pi to pi. What is f of x? It's a naught plus the sum. And please don't be scared of this sum. It's very simple. All of this, of course, dx. Now what's the integral of a naught? As a constant, it's 2 pi a naught plus, then you can insert the integral into the sum. But if you insert the integral into the sum, what do you get? You're getting the sum an integral of cosine plus bn integral of sine, right? All of this is in the summand, and we've just seen here that these integrals, the integral of cosine from negative pi to pi is 0, and the same for this. So basically, this is, you are left with 2 pi a naught. So what we found is that the integral from minus pi to pi f of x is 2 pi a naught. So what is a naught? It's 1 over 2 pi integral from minus pi to pi f of x dx. So this is my formula. This is my formula for a naught. So a naught looks, let's say, not so easy. It's not like the Maclaurin series. Remember, in the Maclaurin series, the a naught is just f of 0. Now we have some kind of integral, but this is it. In this case, this is what a naught is. Okay, so again, remember, our target is to find the a's and the b's in this line here. So we have the formula for a naught. Now what do we have for the other a's and b's? So in my next step, so now to find an. So what do we mean by an? If you expand the sum, this is what you get, okay? You get a1 cosine plus a2 cosine 2x and so on up to a certain point. So now I want to find a formula for an, but for convenience, I will just call it am. What is the m? M is some number between 1 and n, okay? So please, we need to understand exactly what's going on. This m, so if you write your series as a naught and you expand the sum, you will have a1 cosine x plus a2 cosine 2x. Then somewhere you will have am cosine mx and then a big N cosine nx. Okay, so am, if the m was 1, for example, you're talking about this. If m was 2, you're talking about this, and so on. Okay, so this is the meaning of am. Why did we change the notation? So why am I not writing n? You will see. Okay, so we have f of x equals a naught plus the sum. This is what we have. What happens if we multiply f of x with cosine mx? What happens? then you get a node times cosine mx plus the sum, and in the summand you will multiply every term with cosine mx. So now I need to distinguish between the m and n. All of this, right? Okay. So this is what we have. Now let's integrate over the interval minus pi and pi. You will see why again. So when you integrate over negative pi to pi, on the left you will have integral f of x cosine mx dx. What do you have on the right? On the right you will have the first term is the integral, so let's change the color. The first integral is negative pi to pi. The first term is a node cosine mx dx. Now what is this? We just did it, right? So if you look at this page, what is the integral of cosine nx in general? So the n is any number. So if you replace n by m, that's exactly what you get. So basically this is exactly 0. That means when you integrate this thing, this term will be 0. Of course, I'm not writing 0 here because that's after integration, but I'm just explaining it. So when you integrate the first term, you get 0. So I'm writing it here, 0 plus the sum. Now what is inside the sum? We need to distinguish n from m, okay? So n is running from 1 to big N. If you imagine big N as 100, the little n is running from 1 to 100. So this thing, it will go over cosine 1x, cosine 2x, cosine 3x. However, the m is fixed. This m here is fixed. So for example, if the m was 2, then you're multiplying cosine 2x with all other cosines, and you're multiplying it with all other signs, okay? Okay. So now let's compute the integral from minus pi to pi sine nx cosine mx. So I'm computing this term, okay? I'm computing this term. How do you compute this? Now at this stage, I think it's good to remember some properties. We can do it in details using the trigonometric identities, but I rather using the geometric interpretation again. Remember, the sine function is an odd function. The cosine is an even function. If you multiply an odd function with an even function, you get an odd function. And if you integrate an odd function from minus pi to pi, you get 0. So that means when you integrate sine nx cosine mx, all these terms will go to 0 after integration, of course. Okay? So now, this is the sum. This is the sum. So inside the sum, I have bn, this term, and when we integrate, we get 0, okay? Okay. So I think we don't need to write it, right? So it's just 0. Plus. Okay, so we did this integral. We did these integrals. I'm talking about these integrals because these terms, they represent more than one term in the summand. Then I need to integrate this thing. So now I want to integrate from minus pi to pi. Of course, you have the an. Let's forget the an. It's just a constant. I need to integrate cosine nx cosine mx dx. So how do you integrate? Now, unfortunately, I can't argue like before. Before we said the sine is odd, the cosine is even, their product is odd, the integral of an odd function from negative pi to pi is 0. Now, in this case, cosine is even and cosine is even. Both functions are even. So their product is even. When the product is even, you can't say the integral is 0. We need to compute this integral. So how do we compute this integral? We have to go with the identities. So if you remember, what is cosine times cosine? Cosine times cosine, it's half the sum of the two angles. So if you factor the x, plus the cosine of the difference of the two angles. So this is one this is one of the identities that we need to remember somehow when we deal with trigonometric polynomials and Fourier series. I will show you after doing this integral. I will show you the best way to remember this kind of identity. Okay. Okay. So now, what happens when you integrate? After all, this n plus m is just an integer. Okay, and n minus m is just an integer. So again, if you look at the cosine, the left part will be cancelled with the right part, even if you multiply the angle with n plus m, or if you like, you can do the computations. If you don't like the geometric interpretation, then you need to do the integral, do it. So what's the integral of cosine n plus m? It's, sorry, now I want to do the integral. So the integral of cosine is sine over n plus m, plus the integral of cosine is sine over n minus m, and from negative pi to pi, if you substitute the pi or the negative pi into the sign, both give you 0, and this is 0. So basically, again, now going back to here, we are integrating this thing. The integral of this was 0, this is it. The integral of this was 0, this is it. And now, after integrating this, we got 0, right? We got 0. So plus 0. But at this point, I'm sure some of you have noticed something. What is it? If we look at this quantity, what happens when n is equal to m? When n is equal to m, this is undefined, right? So you can't apply, you can't say divide by n minus m, because if n was equal to m, you're dividing by 0. This is completely wrong. So basically, what happens is this. You're adding the terms from 1 to n. As you're going from 1 to n, somewhere you are meeting the m. So at a certain point, this little n will be equal to m. For example, imagine the m was 10 and the big N was 100. Okay, just imagine this. The big N was 100, so you're going from 1 to 100, and imagine the little m was 10. So when you go from 1 to 100, you will say, okay, 1, 2, 3, 4. At a certain point, you will reach 10. When you reach 10, this becomes 10. So the n and the m are equal. That means you can't apply this formula here, okay? You can't apply this formula here. This is where we say, okay, we need to be very careful with this. So let's see what happens. Let's see what happens. Okay, so here, this 0 here, this counts for all the cosines except for the case when n is equal to m. So what happens when n is equal to m? When n is equal to m, you will get the integral from minus pi to pi. Because n is equal to m, you will have am cosine square mx dx. Do you agree? So this quantity here, we get it exactly when n is equal to m. So this becomes the integral minus pi to pi. The am is just a constant. You need to integrate the cosine square. What is the integral of cosine square? It's half 1 plus cosine 2mx dx. As usual, the cosine 2mx will be 0, and what you will have is pi am. Okay? So now I need to delete this. Okay. So after all, like we did before, so now I'm writing the conclusion. So the conclusion is that am is 1 over pi, the integral from minus pi to pi, f of x cosine mx dx. Of course, this is true when m is 1, 2, 3, and so on. So again, these forms, they don't look easy at all. To find am, you're multiplying the function with cosine, then you're integrating. This is not easy, or let's say it's not as easy as the Maclaurin series formulas where we had just derivatives divided by factorials, but this is it now. Okay, now similarly, so if you do the same computations for the b's, so if you want to compute the b's, so to find bm, basically you multiply f with sine mx, then you integrate from minus pi to pi. If you do exactly the same computations, you'll be left with pi bm, and then my conclusion is that bm is 1 over pi integral from minus pi to pi f of x sine mx dx. Okay? Okay. So please, what is, here I like to write the conclusion. So what is the conclusion so far? The conclusion so far is this. If you have a function f of x that has the form a node plus the sum from 1 to big N for a certain big N, an cosine nx plus bn sine nx, like this, then, so if you have this, then you have a node equals 1 over 2 pi. This is the conclusion. These are the red boxes that we added in the two previous pages. So from minus pi to pi, f of x dx, the am, but I'm writing it now as an. You can play with the notations. It's f of x. When we had we had cosine mx, now it's nx. And the bn is 1 over pi integral, from minus pi to pi, f of x sine nx dx. So this is the summary of these computations. So if you have a trigonometric polynomial, this is how you get the coefficients, the a's and the b's. Before going to the, and please notice, we haven't talked about Fourier series yet. So our title was Fourier series, but up to this point, we didn't mention anything about the Fourier series. We're just talking about trigonometric polynomials and how to do these integrals. So before going into the Fourier series, I want to make sure that we understand every single thing here. So let's see a simple example. So imagine you have a function like 2 plus 3 cosine x minus 4 sine 5x, okay? So I have this function. The first thing, I want following these notations, okay? So if you look at this, you compare this with this. And if I ask you what is big N, now what do we mean by big N? Big N is like the last term we reach. The last term, the last value for, sorry. It's the last value for little n. What is little n? Little n is these coefficients. So if you look at these coefficients in this example, what is the highest coefficient? It's 5. So the n is 5. To make it clear, if we ask now what is a node, what do we mean by the a node? A node is the constant term. So what's the constant term in this case? It's 2. What is a1? Again, the an, it's the coefficient of cosine nx. So when you say a1 is the coefficient of cosine 1x. In this example, what's the coefficient of cosine 1x? It's a 3. For example, what's a2? That's the coefficient of cosine 2x. We don't have it. a3, we don't have it. That's the coefficient. Let's write them, okay? So this thing is the coefficient of cosine 2x. We don't have it. a3 is the coefficient of cosine 3x. We don't have it, and so on. So if you agree, all the other a's are zeros. Now, what about the b's? For example, what's b1? Now, what is b1? The bn is the coefficient of sine nx. So basically, the b1 is the coefficient of sine 1x, which is 0 in this example. b2 is the coefficient of sine 2x, which is 0. And What is b5? b5 is -4 because b5 is the coefficient. So this thing here, it is the coefficient of sine 5x, and the coefficient, if you look back, it's -4. Okay, and all the other b's are zeros. For example, what's b6? It's 0. What's b10? It's 0, and so on. Okay? Okay. What about if we want to compute the integral from -pi to pi f of x dx? Okay, of course we can do it. Okay, so we can replace f by its value, and we can do the integral. But this is what I don't want. What I want here is just to make sure we understand the coefficients very well. So if we go back to the summary here, so if you have a trigonometric polynomial, what is a node? A node is the integral from -pi to pi f of x dx over 2 pi. So basically, if you look at this formula and you ask what is the integral alone, it will be 2 pi times a node. So this integral is 2 pi times a node, and in this example, what's a node? It's 2, so basically this is 4 pi. You can check the integral. For example, to make sure we understand the idea, what's the integral from -pi to pi? F of x cosine x dx. Okay? If you look at this integral and you compare it with the an formula, so if you look at this an formula, this is n, this is n. So if you multiply f of x with cosine nx, you're getting an, of course, with division over pi. So if you take n to be 1, that will be f of x cosine 1x, and this is exactly what we're asked to find. We're asked to find f of x cosine 1x. So basically this is pi times a1, right? And what is a1 in this example? It's a 3, so this is equal to 3 pi. This is this integral. Again, you can do the integral just by replacing f with its value and then expanding and doing the integral, but instead now I want to use my new formulas. For example, what is the integral from -pi to pi f of x cosine 10x dx? Again, if you look at this formula here, cosine 10x, that means you're talking about a10. So this will be pi times a10, but in this example, what is a10? A10 is the coefficient of cosine 10x, which we don't have, which is 0. And if you compute the integral from -pi to pi, f of x, for example, sine 5x dx. Now for the sine, so sine 5, that means b5, right? If you compare the two quantities. So now that means this is pi b5, and what is b5 in this example? It's the coefficient of sine 5x, which is -4, so this is -4 pi. Okay, so this is our understanding for these formulas. They help us compute certain integrals like these ones. Again, you can do these integrals the normal way, but I think this one is easier, much easier than the normal way. Okay, so this is the formula. This is we consider this as one formula for the a's and the b's for trigonometric polynomials. Okay, so if you have a trigonometric polynomial, these are the a's and b's equations. Now what about, so the idea of Fourier series if f of x was a node plus the sum n from 1 to n a n cosine nx plus b n sine nx, then we have a node an and bn are as above. Okay, we have these formulas for them. Okay, and we need to notice that the a's and the b's, they depend on f. Okay, their formula, these formulas, they depend on f. Now given an arbitrary function, of course defined on -pi, define, so this is the Fourier series, okay? So define the Fourier series of f by, so now if you have a trigonometric polynomial, again, trigonometric polynomial by definition you have a finite sum from 1 to big N. Now if you have a non-trigonometric polynomial, so you have, for example, x is not a trigonometric polynomial, x squared is not a trigonometric polynomial. So what do we mean by the Fourier series? The Fourier series is exactly this thing, but instead of taking it as a finite sum, we define it as, if we use this notation, so the Fourier series of f will be a naught. The only difference from the trigonometric polynomial is the sum is extended to infinity. Okay, so this is the Fourier series for any function. The only difference again is this infinity. What is a naught? What's an? What's bn? So where a naught, an, bn are given as in the case of trigonometric polynomials. So we still have a naught, an, and bn following these formulas. Okay, so if you have a function, so again this is the idea of the Fourier series. If you have a function defined on the interval -pi, we define something called Fourier series as it's very similar to trigonometric polynomial, but the sum goes to or extends to infinity. Let's see an example before doing anything else. Very simple example. So let's take the function x on the interval pi to pi. And by the way, I will explain everything later, okay? But for now, I want to see the computations. The pi and -pi, are they included in my interval? Is one of them included and the other is not? These little details, I will do them all later. But for now, let's do the computations just to trying to understand the idea. So this is a function defined on the interval -pi to pi. Let's find the Fourier series of f. So what do we mean by the Fourier series? The Fourier series is exactly this series, okay? So we need to find the a naught, the an, and the bn. So all the time to find the Fourier series, all the time we need to find a naught, an, and bn, okay? Now what is the a naught formula? The a naught formula, we need to remember these formulas. So the a naught formula is 1 over 2 pi integral from -pi to pi f of x dx, right? Which is 1 over 2 pi integral -pi. F of x is x dx. And this entails an easy one, x squared over 2 from -pi to pi. You substitute, you get 0. Okay, so the a naught is 0. Of course, we can do the integral, or if you look at the graph of x, so so your function is x. X is like this. This is -pi. Again, what are these points? Are they included or not? We'll do this later. So if you look at this interval from -pi to pi, I think we all agree that we have negative and positive equal areas. So they cancel each other and the integral is 0, okay? So this is the a naught. What about the an? Now, what is the formula for an? It's 1 over pi integral -pi to pi f of x cosine nx dx. So it's 1 over pi integral. Now, between -pi and pi, what is f of x? It's cosine times x times cosine and x dx, okay? Now, how do we compute this integral? Clearly, this is done by parts, integration by parts, because you have a trigonometric polynomial a trigonometric function cosine times x. So you can do it as integration by parts. Instead, I like to do it quickly like this. We all agree that the x is an odd function. The cosine is an even function. So if you multiply an odd with an even function, the result will be an odd function. And if you integrate an odd function from negative pi to pi, you always get 0. Check that, okay? So if you do the computations using integration by parts, you will get 0 for sure. So the a ends, so what we're saying now, what we're saying is the a node is 0, and also the a ends are zeros. So all the a's are zeros. Now we need to compute the b's. So what is bn? Bn formula is 1 over pi integral minus pi to pi f of x sine nx dx. Now for this integral, the x is odd, the sine is odd. The product of two odd functions is an even function. If you have an even function, you can't say 0. So the integral now is not 0. We need to do it. We need to compute it. However, because it's an even function, we can multiply with 2 from 0 to pi if you agree. This is not a big deal, but again, to make it clear, this is odd, this is odd. The product of odd is even. When you integrate an even function from negative pi to pi, it's 2 times the integral from 0 to pi. I will write these summaries later, okay? The properties of odd and even functions. Okay, so now we need to compute the integral x sine nx. Unfortunately, we need to do it. This is integration by parts, right? So now here, we need to do the integral. We can't avoid it. So I'm going to do u dv integration by parts. So u is x, the dv is sine and x. We differentiate, we integrate, then we differentiate again, we integrate again, right? Remember integration by parts, you multiply this, you multiply this, you multiply this, plus, minus, plus integral. Okay, so this is how we do integration by parts. So what does this mean? This means you multiply the first arrow, the first orange arrow, it will be negative x cosine and x over n. So this will be negative x cosine and x over n. The next term will be plus sine and x over n squared. Of course, these limits are from 0 to pi, and don't forget that you have a 2 outside, right? This is your integral, 2 over pi, sorry. Okay, now we substitute these limits. So you substitute the upper limit minus you substitute the lower limit. When you substitute the upper and the lower limits into the sine term, this will be 0 because sine and pi is 0 and sine 0 is 0. So we don't care about the second term. What about the first term? So this will be 2 over pi. When you substitute the pi, it will give you negative pi cosine, cosine and pi over n, minus when you substitute the 0, you get 0, right? So this will be, the pi is cancelled, so this will be negative 2 over n cosine and pi. This is what? This is the Bn formula. Now what is cosine and pi? When we say cosine and pi, just here to explain it. So cosine and pi. When n is 1, that's cosine 1 pi, that's negative 1. When n is 2, cosine 2 pi is positive 1. When n is 3, cosine 3 pi is negative 1, then 1, negative 1, and so on. And if you agree, this form, negative 1, 1, negative 1, 1, I can write one formula for it. It's negative 1 to the n. So from now on, whenever we have cosine n pi, when n is an integer, this will be, so negative 2 over n. And what's cosine n pi? It's negative 1 to the n. And now you have two negative signs. This is negative, because this is negative 1. And this is negative 1 to the n. When you multiply, the exponents are added. So this is basically 2 times negative 1 to the n plus 1 over n. So this is the final form for Bn. Okay, so remember the question was, we had the function x. This is the function x. The question was to find the Fourier series of the function. We computed all the a's, they were all zeros. Then we computed the Bn, and this is the Bn. So now what's the Fourier series? After finding all these numbers, what is the Fourier series? This is the Fourier series. So the Fourier series is A node plus this summation. But in my example, the A node is 0, the An is 0. So basically, so I'm writing it just to make it clear. So in my example, the A node is 0, the An is 0. So basically what's left is the sum from 1 to infinity. What's the Bn? It's 2 times -1 to the n plus 1 over n sine nx. So this is the Fourier series, okay? This is the Fourier series of the function. Okay, so what's the summary of this example? We started with the function x. We did all the computations. We reached this form, the Fourier series. Now, what is the geometric? This is very important. So the geometric meaning of the Fourier series. So in our example, we had the function x. We found its Fourier series. It was 2, the sum from 1 to infinity, -1 to the n over n sine nx, right? This is what we found in the end. If you expand this sum, what do you get? You get 2 times. So when n is, sorry, this is n plus 1. So when n is 1, you get sine x. When n is 2, you get minus sine 2x over 2. When n is a 3, you get a plus sine 3x over 3, and so on, right? Then you get a negative sign, positive sign, negative sign, and so on. Let's try to understand the geometric meaning of the Fourier series. The idea is if you plot the function f of x, so if you plot the function f of x, and it's, and the partial sums of the Fourier series of f. So what do we mean by the partial sums? The partial sums mean, so you look at the Fourier series, it's an infinite sum, it goes to infinity. So if you take the first term, let me call it S1, the first term of the Fourier series, what is it? It's 2 sine x. Then it's not the second term. If you take the first and the second term, it's 2 times sine x minus sine 2x over 2. Then if you take as a 3, which is the first 3 terms, it will be 2 times sine x minus sine 2x over 2 plus sine 3x over 3, and so on. So I think now the idea is clear. Now the meaning of the Fourier series, if you plot the function, and these partial sums, so in this example, so this is negative pi, this is pi. What is the function x? I think we all know it, right? This is the function x. Y equals x between negative pi and pi. Now, if you start plotting the, so if you have a graphing calculator, for example, if you start plotting the partial sums, so 2 sine x, how do you draw 2 sine x? 2 sine x, we know it, right? It's sine x, but it's multiplied with 2, so it goes up to 2 here. So it will be something, let's say, like this. So this is what? This is S1. Fine. Let's plot S2. What is S2? It's 2 times sine x minus sine 2x over 2. Now, don't worry, okay? I don't know how to draw it. We need a calculator. We need a software to draw it. Don't worry. But if you do it, it will give you a certain graph, right? Then if you plot S3, it will give you a certain graph. If you plot S4, S5, S6, and so on. So after plotting many of these S's, you will see something. You will see that the graph is getting closer and closer to the original function. Something like this. So if you keep plotting, so let me call this, for example, as n, okay, for large n. If you try again, just use a calculator use Mathematica, use MATLAB, use anything, Google any website that can graph these things. So if you put the first function, you get something like the blue function. If you plot the second function, you will get something. For example, you may get something like this. For example, it's not necessarily exactly like this. But as you move on, as you're taking more and more terms of the Fourier series, your graph will be very, very close to the original graph. For example, and I assure you, if you take the first 100 terms, I'm sure, so I'm making this a little bit bigger than the previous ones, okay? So if you take the first 100 terms, I'm sure, I assure you, and you can do it, you will get something like this. So I'm sure if you take S100, this is what you get. So this is the meaning of the Fourier series. So what's the meaning? If you plot f of x and the partial sums of the Fourier series, okay, Sn, the partial sums, will be very close to f of x as n gets bigger and bigger. Okay, this is the meaning, this is the geometric meaning of the Fourier series. If you plot the function and the partial sums, things are getting closer and closer. Again, I will explain later what about these endpoints, are they included or not, and what about outside the interval. So this is if we're taking the function on the interval negative pi to pi, but what about if we extend the graph outside this interval? I will do that.